Hello everyone, my name is Xinyu Chen. I'm a GSI for this course CS188, and I will be recording exam preparation sections for this semester. So if you haven't known this before, so basically for this course, there are two types of discussion sections. One is regular discussion sections, where we will discuss basic questions that kind of review the materials from the lectures. So the difficulty of problems discussed in this section will be more similar to regular homework assignments. Then for exam preparation sections, we will discuss questions that are more similar to the difficulty of problems that may appear in the future exams. So usually these problems will be harder than the problems discussed in regular sections. If you did not make it to any live discussion sections, or if you want to review the material, please watch this video. And if you have more questions, feel free to come to my office hours. It is 3 to 5 p.m. every Thursday. So let's get started. For this week, we will mainly discuss about questions related to search. This includes how to formulate a problem into a search problem, and also it includes some basic search algorithms. So let's look at the first problem first. It is about N queens. So N queens is a pretty classic search problem. So from the problem statement, we can see that the general goal is to place N queens on N times N chessboard so that none of these queens can capture any other. So what do we mean here? From the caption of figure 1, we see that queens can move any number of squares along rows, columns, and diagonals. Then let's say if we put a queen in the leftmost column of the second row, then this moving rule means that we cannot put any other queens in the same row of other columns or in the same column of other rows. And also we cannot put other queens in like same diagonals as the current queen. So this is basically kind of some like rules of this problem. Then let's look at the part A first. So in part A, we need to like formulate N queens as a search problem. So we need to think about the start state, goal test, and successor function. So let's look at the start state first. So it is relatively straightforward. So the simplest way to think about it is to like basically at the beginning of the search, if we haven't done anything, then what's the state should be like. So for N queens problem, it should be kind of just an empty board because there's like nothing on like chessboard before we put any queens there. So this is the start state. Now what is the goal test? The goal test means that when we like reach a valid solution, we don't need to like expand the current state anymore. We can kind of find the answer in the problem statement, because here we know that for 8 queens puzzle, we need to like place queens such that none of them can capture any other. Then for general N queens problems, it just means that we need to place N queens on an N times N chessboard such that none of them can capture any other. So this is the goal test. Then how about the successor function? For the purpose of part A, we see that there is a note saying that we will allow boards in our state space to have any configuration of queens, including boards with more or less than N queens, or queens that are able to capture each other. It means that we will start with the simplest version of the state representation, where our state space could also include many invalid states according to the N queens rule. So basically, one way to design the successor function is to allow like one more queen to be placed on like arbitrary positions of the chessboard. So let's say when we start with this empty grid, we can first like put the queen in arbitrary positions. Then then for the next state, we can still put the queens in arbitrary position. Like here is an invalid like way to put the next queen, but for the purpose of designing the state space and also the successor function, for now we just consider all of them as like possible next steps, although we know that some of them will never lead to the solution because it already violates the n queens rule. Okay, so this is for part A. Then in part B, we are asking how large is the state space in this formulation. So basically, this formulation means that refers to like part A description, saying that basically the state space we do not need to think about any rules at this moment. Then this effectively means that given like a chessboard with like n times n grids, if we ignore any like moving rules of the queens, then it means that for each grid in the chessboard, it will have two possibilities. One is that we put a queen in that grid. Another is that we just put nothing. So if we think in this way, then the number of states in this state space will be 2 to the power of n squared. Yeah, because we see that there are n times n like n square grids, where each of them have two possibilities. Well, then we can notice that this state space is too large because it includes so many invalid states. So we will try to reduce the state space in the following parts of this problem. Let's look at the part C. Part C is asking us how could we reformulate our successor function to reduce the effective state space size. So earlier we said that for when we design the successor function in part A, for like each state we could still like put like another queen in arbitrary positions, ignoring the moving rules. So here, one way to reduce the effective state space size is to like kind of restrict our moves so that it will only put queens that satisfy this requirement, and none of them can capture any other. So basically, it just means that here our successor function only returns legal boards, ignoring those like invalid moves. Then, following this idea, we can think about a more efficient state space representation. So earlier we are kind of like representing our state space according to the presence of queens in each grid of the chessboard. However, from the rules, we already know that at the end we can only put n queens in these n times n grids. And also, an important observation is that in all legal states, each row or column will have at most one king, or otherwise the queens will attack each other. So following this observation, an alternative way to design the state space is to mark the position of n queens for state representation instead of mark like the presence of queens for each grid. So what do I mean by this? So we can basically instead of like putting like n queens in an arbitrary order, we can kind of put the n queens from the leftmost to the rightmost column. So this means that we will only like for example, for the first step, we will put one queen in the first column, and then we will proceed to put queens like to the right of the current queen. Then we can see that for each queen, when we decide to put it in the grid, then it will have like n options, like row 1 to n. Like for the first queen, it could be put in like in like a row 2, the second queens to be put in like a row 4, etc. But to design a state space, there is also one option of like 0. So 0 means that we haven't put the current queen first. For example, for the current state, we haven't put like the third and the fourth queens yet. So basically, it is marked as 0. So basically, for the state, I have like shown here. It could be represented as like a 2, 4, 0, 0. So this is a possible state according to this state representation. Then, according to this state representation, our answer will be n plus 1 to the power of n, because like we know that there are n queens and each of them has like n plus 1 options. But notice that so definitely this new state space is much smaller than the previous state space, including like 2 to the power of n square states. But still, we can see that it is not the most efficient way of to represent the states, because as we can see here, for each bit, like even if, like for example, even if we have put the first queen in the like second row of the leftmost column, in the second for the second column, effectively we can still put the queen in the like second row according to this state representation. So definitely there will be a better answer than this like n plus 1 to the power of n. So for better solutions, feel free to like look at the official solution that will be released. And also, I think even for the official solution, there may be a better like a better number, and feel free to think more about it. And you can also discuss with us if you have any thoughts. Then let's move on to the second question about search. In general, I think the exam preparation section for this week is a bit ahead of the lecture. But I think after this week, maybe after the Wednesday or Friday's lectures, the professor will cover the different search algorithms that we have that are listed here. So so basically for this question, it kind of it is trying to ask about the differences among like a BFS, DFS, and UCS. So these are 3 pretty basic and classic search algorithms. So before we look at the problem statements, let me kind of briefly summarize these search algorithms first. So take this graph as an example. So basically, BFS stands for breadth first search. So what do we mean by breadth? Breadth just means that like for each like depth of the like graph. So basically for the graph we have two for this example we have 2 special nodes. One is S, it is the start node. One is G, the goal node. Then there are several nodes between S and G, and our goal is to find a path with like the shortest cost from S to G. So basically, breadth just means that we will just consider like how many nodes are in like the same depth of the graph. Here, depth is computed according to its like the number of edges between the start node and the current node. So then, what do we mean by breadth first search? According to its name, it just means that we will like search for the nodes in according to like the it's like basically we will search for nodes in the same depth first, then proceed to the next steps. So basically, starting from S, firstly we will always select the the edge to A, because it is the it is like only one edge after the start node, and also its cost is very low. Then after we explore the node A, then next we will explore the node B, because like they are in the same depth, so it is like so basically means that we will explore the nodes according to the breadth first. Then we will from A we will proceed to C, and from B we will proceed to G, and finally from C we will proceed to G. So then we can kind of cover the two possible passes here. So basically the order is S first, then AB, then CG. This is a breadth first search. Then what do we mean by depth first search? Depth first search means that we will explore the nodes based on its depth. So it will keep going for the deeper nodes first. Then it will backtrack to explore other options. Then for this same graph, it means that again we start with S. Then we will move towards to A. Then here we will not go to B, because we want to explore deeper nodes first. Then we will go to C, then G. Then we will backtrack to C, but there's no other nodes after C. Then we will backtrack to A. Again, there's no other options. Then from S, we know that there's another option called B. Then from B, we can go to G. So this is basically the depth first search. Finally, UCS stands for Uniform Cost Search. So basically, for the previous breadth first search or like depth first search, it doesn't. It will consider like breadth and depth as a more important factor of considering the priority than like the cost of the edges. So basically, for UCS, it mainly concerns about the cumulative cost of each passes. So what do I mean by this? So again, start from S, then we will explore A first, because we know that the cost of A is S2A is 1, but the cost of S2B is 2. So A has so this pass has the lowest cost. We need to explore it first. Then for the next step, there are kinds of two options that are equivalent to good. One is that we can move forward to C, because at the point of C, the cumulative cost is 2. And also then the next option is that we can also proceed to B, because for B, the cumulative cost is also 2. Then between B and C, we will choose to expand C first, because we can see that from C to G, the cumulative cost is 3. But then for B to G, the cumulative cost will be like 4. So basically, this is the idea of a uniform cost search. It will prioritize the passes that have lowest cumulative costs for search. So one important observation is that when all edges share the same positive costs, UCS has the same effect as BFS. Because for BFS, we can just think about it as that it will prioritize the search for like for shallow nodes first before it explores to like deeper nodes. So basically, if all edges have a weight of like 1 or 2 or the same number, then they will just share the same effect. Okay, so based on these understandings, we can let's see whether the algorithm remains equivalent if we add additional cost C to every edge weight. So actually for BSFS and DFS, for the purpose of this course, we usually ignore the edge costs when we perform these search algorithms. So they're solely based on the breadth and also they kind of solely based on the positions of the nodes in a graph. So effectively, the answer for like BFS and DFS is that it will always be equivalent no matter what we do for the cost. But actually, I want to say that even if we consider a more advanced way of BFS and DFS, which means that when there are like two nodes with the same depth or like the same position of or like the same positions. Let's say if we want to prioritize the nodes with a smaller edge cost, still because we can see that for BFS and DFS, it do not consider cumulative cost in any case. Then let's say C1 and C2 are the original cost of the individual edges. Then when we add the same constant C to them, still the priority holds. So basically it means that let's say if we want to make the cost to like from 1 and 2 to 11 and 12, still we will search the path from S to A first because like this order doesn't change. So for BFS and DFS, the answer is definitely yes in any case. However, for UCS, it is a different story. Why? The key thing here is that for UCS, the number of edges for different passes will be different. So when we try to compare the cumulative costs, the order may change if we add additional cost to each individual edge. So let's again look at this example. So let's say if we want to add a C equals to 10 to every edge, then we can see that initially like initially S A C G is better than S B to the G because initially like 3 is smaller than 4. But when we add this cost to every edge weights, then things change. Then in this case, S to the B to the G becomes better because like S to the A to the C to the G is 32, but S to the B to the G is 24. So basically, in this time, this path is better. So basically, the idea is that when the additional cost C is large, it will kind of change the ordering of the cumulative cost for different passes. So this is why for UCS, adding additional cost per edge will kind of change the solution. But how about if we multiply a constant W to every edge weight? Again, for BFS and DFS, the answer will be yes, the solution doesn't change in any case. But this time, for UCS, the solution will also not change because we know that let's see if like C1 and C2 are the cumulative passes, the cumulative costs for each pass. Then when we multiply it by like positive constant, then this order still preserves. So like let's say when like when this W is still like 10, so initially like 3 is smaller than 4. After this multiplication, 30 is still smaller than 40, right? So this time, the answer for UCS is also yes. Okay, then let's look at part B. Again, we are trying to like think about the equivalence among different algorithms in some special cases. So here still like when we consider two such algorithms to be equivalent, if like if all the states are expanded in the same order and return the same path, and assume like all graphs are directed and acyclic. Assume we have access to we know that in some way if we when we assign the edge costs, then UCS will be equivalent to BFS. Then how should we design a way so that UCS is equivalent to DFS? If you still remember the discussion about these search algorithms that we briefly discussed before, then this question will be pretty easy, because we just said that when all edges share the same positive cost, like 1, UCS has the same effect as BFS. So from this observation, we kind of know that C equals to 1 is not the answer, because this will be equivalent to BFS instead of DFS. Similarly, this will not be the correct answer, because if we assign the same weights, then it is still equivalent to running BFS, and BFS is definitely not equivalent to DFS. Then this answer will also not be correct from the previous discussion, because when we put an arbitrary alpha here, it means that alpha should be this equivalence should hold for any value of alpha. But a very trivial solution is that when alpha is equal to like 0, then definitely still it is not equivalent. It is still equivalent to a BFS, and it is not equivalent to BFS. So this is also not the correct answer. Then actually C equals to 0 is definitely not a good answer, because when all the like edge costs are 0, it means that basically all nodes are equivalently good to expand. So it is definitely not a DFS where we want to prioritize like deeper nodes. Then finally, the question is whether this is the correct answer. The answer is that we indeed want, this is indeed the solution, but let's see why. So this is like the graph we constructed, which is which could make like UCS equivalent to BFS. So let's see if we kind of put like add like a negative sign to each edge, what will happen? So again, from the start node S, we will go to A first, or A or B first, because these are like the only like nodes that are directly connected to S. But then here, instead of exploring B next according to BFS, indeed we will explore C first, because if we look at the cumulative costs, like here like -2 is smaller than -1. So basically it means that the deeper the node is, the lower the cost is. So definitely we will prioritize like deeper nodes first. So in this case, we will know that by adding a negative sign, we will make this algorithm equivalent to DFS. So this is the answer. Okay, let's move on to the third problem. As you can see, the problem description is pretty long. So usually when every time when I see the general problems, such a long general problem statement, I will read the description of the sub problems first, so that I can kind of understand which parts I should focus on in the general problem statement. So let's take a look at the problem A first. So here the setting is we can have because in the general problem statement it says that there are like a number of p of SpongeBob's cars, but basically A is considering a special case where we only control one car. So and then in this case, the question I is asking, what is the size of the state space, and also it is asking for a tightest upper bound instead of like a pretty loose bound as we've seen for the n-queens problem. And the goal here is that we need to search for a sequence of actions that guarantees a Pac-Man is caught no matter where Pac-Man is hiding. And also, from the general problem statements, we already see that we have absolutely no information about where Pac-Man is hiding, but the good thing is that Pac-Man has to stay stationary. So basically, we can just move our cars to visit all the possible positions in this Pac city. Then we can guarantee to catch this Pac-Man. So let's see how to compute the size of state space. To compute this size, a good practice is to kind of factorize the state space a bit, so that we can understand which components are important to represent a state in this state space. So for this problem statement, the good things to start with is that at least the state space should represent the status of the car. So what are the important attributes of the car? First of all, definitely we need to know the position of the car. Then we can see that the dimension of the city is n by n. So basically all the positions have like n times n choices. Then for the cars, there are two additional attributes. One is the speed, and from the problem statement, we know that the speed could vary from 0 to 6, and also according to the possible actions here, we know that all the speeds should be integers. So basically, there are like 7 choices here. Another attribute is the direction of the car. So you can see that from the action space, it could turn left, go straight, and turn right. So it means that there will be 4 different directions corresponding to like north, south, and east, and west. So basically, to compute the size of the state space, firstly, we need to consider like the car positions times speed times direction. So recap that it is nm times 7 times 4. But the remaining thing is that we need to guarantee Pac-Man is caught. So to make sure of this point, we need to keep track of the positions that the car has visited and make sure that it covers every possible position in this Pac city. So basically, we also need to time state size, place size with a number to keep track of the visit status. So for this number, it should be 2 to the power of mn. It is kind of similar to how we represent the state space for the n-queens programs. Basically, for each position, we'll have like 2 choices. One is that we have visited it, another is not. Then there are like n times n possible positions. So this number is exactly this. Then when we multiply all of them, we get our final answer. Okay, so this is the this sub question. Then the second like the question I is asking, what is the maximum branching factor? So what do we mean by branching factor? So it means that basically how many actions we can take for each state, and we need to consider the maximum number of actions here. So actually, when we look at the problem statement, some people may kind of confuse like how to compute this like branching factor with like how to compute the state space. So earlier we see that there basically positions are directions. Positions, directions, and speed are like the attributes of the class. But actually, here when we are computing the maximum branching factor, we need to consider what are the actions we can take. So there are two types of related actions, two kinds of like operations that are related to how we should compute the actions. One is the throttle. So you see that there are like 3 options here. Another is steering. Again, there are 3 options here. So basically, to compute this branching factor, it is kind of the number of possible choices for throttle times the number of possible choices for steering. So for this question, it's like 3 times 3 equal to 9. Then the third question is which algorithms are guaranteed to return a path passing through all grid locations on the grid if one exists. So it is one way to think about it is to like is to see like whether the search is complete in some sense. So let's start with a brief discussion of what are the differences between tree search and graph search. To me, the easiest way to understand it is that for graph search, besides the current state, the search also maintains the set of expanded states, so that graph search guarantees that the search never expands or visits a state twice. And a related notion of this like graph search is called a closed set, which means the set of expanded states. So we may cover this definition in the later part of the lectures. But compared to graph search, tree search doesn't keep track of the states that have been visited, so it may visit the same state twice. Then from this, we can kind of know that both depth first graph search and breadth first graph search will guarantee to return a path, because it is guaranteed to visit every state and from no more than once. So essentially it could and also we can see that our state space is finite. So it will definitely guarantee to provide a solution, a path that passing through all grid locations. So it means that it will definitely catch the pacman no matter where the pacman is located. The third related comment is that the breadth first search is kind of complete, because it will always search for the passes in the increasing order of its like the number of edges between the start state to the current state. So and we can see that from all possible states of this problem, that definitely we can kind of know that for each state, what are like the minimal number of steps we need to take from the start states. So which means that when we use like the breadth first tree search, or usually we'll also call it just call it BFS by default. So basically this is also also guaranteed to return a pass. Then the question is why depth first tree search may not guarantee to return a pass. Notice that when we represent the state, there's an important component called like visit status. So basically, it will keep track of the two power of mn like possible representations of the visit status. So we can see that if the car visits a state that it has visited before, then the representation of this visit status will not be changed after an action, and because for depth first tree search, it will just keep going in one direction to deeper nodes. Then it may not guarantee to visit another path that will lead to a valid solution, and it may just keep kind of get checked into an infinite loop when it tries to find a path. So this is why depth first tree search is not guaranteed to like return a desired solution. Then the fourth question is kind of related to the third question. Is breadth first graph search guaranteed to return a path with the shortest number of time steps? If it exists, the answer is yes, because it always searches for like passes with shorter number of time steps or a shorter number of edges before it moves forward to search for like longer paths. Finally, we want to see that when the number of cars is p instead of 1, how the results of a previous setting of a single car could change. So first, let's recompute the size of the state space in the case of p cars. Firstly, recall that when there's one car, to compute the state space, we need to enumerate all possible options of the car position, speed, direction, and the visit status. Then suppose the answer of N1 is here, so this is consistent with our like previous answers. Then in the case of P cars, definitely we need to like enumerate car positions, speed, and directions for all the P cars. So there is a power of P for the like first three components. But notice that in this problem setup, we only need to make sure that one of the P cars catch the Pac-Man. This means that when we check the visit status of the cars, we only need to do it once for all the P cars instead of checking the visit status per car. So basically, the last component is still 2 to the power of mn. So in this case, the answer of this question is none of the above. Then let's see how the results change for branching factor. Recall that in the case of one car, we need to enumerate all the possibilities of throttle and steering. Then when there are P cars, the answer BP will be B1 to the power of P, because we need to enumerate this for all of the P cars. Thanks for watching this video, and if you have more questions, feel free to come to my office hours.